the papers we've been discussing in group meeting. It's like, oh, wow. I guess I picked the right ones. One thing I was thinking is, since I have the distinction of starting this session, which this is the AI session, if you're interested in DFT, it's next door, just so you know, that we will be dense, but I don't know about functional theory. But speaking of being dense, I thought I would start with just a quick overview of machine learning and generative modeling, which maybe is unnecessary. Now, how many people here know what a GAN is? How many people here didn't raise your hand? This is funny because that didn't add up. Okay, so that's actually that's better than I was expecting. I was wondering if through the morning session some people are getting lost. So I'll go through this quickly. This is machine learning. X goes to Y, right? We want to make a prediction about X. For our model, there's all sorts of choices, but we're going to be talking about neural networks, which takes those X values and computes nonlinear functions and mushes them together, and this is very powerful. And if you have more than one of these hidden layers, it's called deep learning. And that's really the definition. Look it up, at least according to the leaders of the field. And the way we train this is we just give it an example and make some prediction, and it's either right or wrong, and depending how wrong it is, we backpropagate that loss. So basically, this backpropagation algorithm assigns blame for getting the wrong answer to every weight in that network and tells you how to update it. And you just keep doing this and been very successful. This is a picture on the right. I'm gesticulating without the laser pointer. This is actually my building where I work, and this is a Uber self-driving car back when they were still on the road. And we have concrete barriers here, so that's nice. This is literally driven by deep learning. Go is driven by deep learning. This is speech recognition. This was at GTC. This is a deep learning thing that's looking at my facial features and coming up with a little sad emoji because I'm frowning, right? And so it's all through our society. And a lot of what we've been doing are discriminative models, right? So given a picture, is this a face, right? And you go on Facebook, it identifies the faces and it tells you who it is, right? And with a generative model, it's the other way around, where what we're outputting is the input of the discriminative model. We're actually outputting a face or a molecule, right? Which begs the question, what goes here? A lot of choices there, but the simplest is just some random distribution, and you're mapping that distribution onto the distribution of faces or cats or whatever it is. So how do you train this, right? Because this is, for the discriminative, you have a data set, you have a Y, you know what the right answer is, but how do you say this is in fact a picture of a cat? That was the whole reason you were training the discriminative model. And that's where generative adversarial networks or GANs come in, where you solve it with another neural network. So you have your generator, it's producing, this is actually a picture of a bighorn sheep that Google thought was a dog in my phone, and this is a picture of my dog, right? And so the discriminator looks at these and it says this is a real dog picture or not, and you can use that as a loss for fixing your discriminator, and you alternate training these, right? And this actually works. So this is fun. This was the seminal paper, 2014. That's 4 years ago, right? 4,339 citations last night. I checked again this morning. There was 50 more. And this was what they did. So these are kind of faces, right? They have 2 eyes, they have a nose, they have 1 or 2 mouths. They kind of look like faces, right? And you go in a year, they got colorful. They're starting to look like Donald Trump. And if you go to this year, just 4 years, this is earlier this year, right? We're generating faces like this, right? Which are not perfect. If you look very carefully, especially around the ears, you can see a few glitches, and these are cherry picked as you start looking at the broader set. There's some weird things in there, but this is very impressive. Why can't we do this for molecules, right? This is not a machine learning conference, this is ACS. And so this is a question, can we generate molecules? And what we're interested in is structure-based drug design. I don't know, maybe with this audience, you know more about GANs than you do about structure-based drug design, I don't know. But structure-based drug design, where we actually have the 3D representation of the receptor, of the ligand, how they fit together. We want to be able to predict what the pose is that ligand binds, whether it binds or not, ultimately actually how well it binds, right? And we can use this for virtual screening, identifying hit compounds. If we have a hit compound, we can use it for lead optimization, where it becomes very important to do this affinity prediction and not only make predictions, but actually map it back on and explain the predictions, right, to guide the medicinal chemistry. And a traditional drug discovery funnel is something like this, where you start with some chemical space, tens of millions of purchasable, where we talked about enamine this morning, with accessible, synthesizable chemical space and much larger. And then you do some fast matching algorithm. This is a shameless plug. If you are still around on Thursday, I have a talk in the morning, so you can still make your flight on Farmit, which is a website for doing really fast pharmacophore and shape matching. If you can't make it, just go to the website. That's really the whole point of the talk, is to get you to go to the website. But once you've narrowed it down to a more tractable set, you want to actually score and rank these, right? And for structure-based design, classically, you're looking at pairwise interactions between atoms and the receptor and the ligand, and you have some empirically defined scoring function to produce some delta G or something. What we want to do is we want to use machine learning. So we take the 3D structure of the protein and the ligand, and we want to actually evaluate, is this a good pose? Does it bind? How well does it bind? And what we're using are convolutional neural networks. So the convolutional part of this is it just takes a little piece of the image and computes a nonlinear function of that, and that produces an output in a feature map, and then it moves over and produces another and another and another one using the same convolutional kernel, right? And you learn many of these and learn many feature maps. And what these are learning are features. For example, a low-level feature might be a horizontal edge, a vertical edge, or any edge. Right? And this is what a feature map might look like. And then you could put these together to learn higher level features like a corner or a more sophisticated shape. Right? That's in an image. We don't have images. Images are 2D pixels of red, green, and blue values. Right? What we have is a 3D image. This is how we're representing our complexes. It's just a 3D grid where each voxel is what atoms are in that position in space. Right? So our goal here is not to excessively featureize the input. It's to give as basic a representation to the model as possible, because it's worked very well with image recognition. So it's just, what's the resolution of your grid? How exactly are you defining whether an atom's there or not, and what atom types do you care about? So why grids? Because there's actually some really horrible things about them. The worst thing is it's coordinate frame dependent, right? So if you rotate a molecule in your coordinate frame, the grids, all these grid points change, and it's different, and the model sees something different, and it will give a different prediction, which obviously it's the same molecule, and that's wrong, right? That's a con. And we really aren't traditionally, we look at pairwise interactions in scoring, right? And we're not making those explicit, whereas if you're using some distance-based representation, you won't have these problems. On the flip side, all the spatial relationships, whether they're pairwise or something much more sophisticated, are right there, right? It's a 3D picture. And it's embarrassingly parallel. You can put this on an NVIDIA GPU and it just streams, and it's a 3D picture. So it's easy to interpret things. You can put things back onto that grid and look at them in PyMol. And this is the sort of model we use. It's fairly straightforward. It's 3 layers of pooling and convolution, and we generate a pose score, whether this is a good pose or not, in an infinity. And here are some results. There's a ton more results in these posters. These are the same poster. You can either come 8 tonight, or at SciMix, or 6 p.m. tomorrow. So another shameless plug here. If you want to learn a lot more about this approach, you can come both nights too. I mean, that'd be great. But we're doing okay. Compared to our baseline VINA and these retrospective evaluations, we are way, way better sort of across the board. But this isn't really what I said I was going to talk about so many months ago when I thought we would be farther along. What I was going to talk about is generative modeling. We want to go beyond just scoring. This is very much feed forward, right? It's like, here's the picture, tell me the affinity. We want to go back to that molecule. And so one way to do that is just through this backpropagation approach. Only, if you remember, when we're training it, backpropagation is saying, looking at the output and loss and telling you how to change the model. If we have a trained model that we like, we can not update the model, just keep going. and update the input to create an input that has a better output according to the model. And if you do this to images, you get something like this. So you start with just this picture of noise, and they're optimizing it for a certain class of image. Anyone guess what? Bananas, thank you. No one ever says that. All right, but I'm glad you saw that. I see bananas too, but there's elongated yellowness here, but I think we all realize this is not an actual picture of bananas. However, we need actual ligands. And so the way we do this, well, so here's what happens when we backpropagate in the grid. You have something like this that says, I want more oxygen here, which makes a lot of sense. There's an arginine right here. I mean, it makes you very happy to see this because it matches your physical intuition, which, believe me, these things don't always do. And it says less oxygen here, which if you look carefully, it makes sense with what's happening in the receptor. If you really look more carefully, you realize it really makes no sense because the ligand doesn't actually have any oxygen there. It's 0, so you can't have negative oxygen. But of course, mathematically, the grid, the network doesn't realize that. So we want to keep backpropagating to where this is actually physically realistic. So the way we do that is we are maintaining all the atoms. So for this part, we aren't changing the chemical matter. We're just changing positions of atoms. So we backpropagate chain rule onto the atom centers with a force vector, and it becomes a vector quantity saying this is how you move this atom in order to maximize the output of your network. And then we can just use traditional standard minimization, energy minimization approaches. And this is the very first time we did this. Some of you may have seen it. It's not going to change because it's always going to be the first thing we did. And here's what happens. Watch closely. Did it move? Oh, it moved on here. Yeah, good. So it pulled this ligand in. It's actually clashing with the receptor here. And I'm coloring it by the model's happiness with the atoms. And you saw, and if you look, it looks like it actually got redder, but actually the score did improve. There's no bugs here. This is a higher scoring pose. And why it likes it more is it has these electrostatic interactions, or why it appears to like it more, and it just pulls them too close. Right? So it hasn't properly learned to balance steric clashes with electrostatics. And this actually makes a lot of sense because when we trained it, they were all realistic poses. We never showed it something with overlapping atoms and said, this is horrible, right? You should never do this. And so when we went and actually just took a set of low RMSD poses, they're from 2 to 4. The gray here is if you, the distribution you get if you minimize them to the perfect crystal structure. And most of them got worse using our first model, right? So we're generating new poses, but they're bad, even though the model likes them more. But these are the most informative examples here. They're cases where the model likes something that's wrong. So we just mix these back up into our training set, and we just iteratively refine our model, right? And we're shifting this left. Now, I wish it was over here, but it is shifting it left, and it's more like what you see with an empirical scoring function in terms of distribution. And so if I take this updated model and apply this to the same molecule, and it was moving already, okay. It's not doing it on my screen, but, right? Now it's not inducing steric clashes, it's wiggling around there. It's more of a traditional minimization looking thing. Right. So this is generating poses of an existing molecule. We're not changing the molecule. This is one thing we can do. The more exciting, interesting thing, for a number of reasons, people have already mentioned, this opens up a wider chemical space, and it's just really interesting to see if we can do it, is can we just generate sort of from scratch, de novo, a molecule for a receptor, right? Given we have a generator, there's a number of interesting things we can do with a generative network. Autoencoding is probably the simplest. You start with the ligand. Here we're representing everything as a 3D grid. You encode it down to this latent space, which is just a vector of numbers. And then that represents this ligand in a way the neural network understands, and then you can regenerate it back. And so the idea is the output matches the input, right? And so there's a number of ways you can train this, but the simplest, you could just do an L2 loss, just a mean squared error. Are you generating what you put in? Yeah. And this seems kind of pointless, but what it does is it's creating this continuous latent space. And there's really interesting things you can do there. This paper was already referenced 3 times this morning, it's worth referencing again because it's really cool. If you haven't seen it, you should go read it, where they do this auto-encoding. Now, this is on 2D smiles, but you have this latent space, and there's all sorts of interesting things you can do in this continuous space. So that's auto-encoding. Something a little more sophisticated is context encoding. So this isn't you give it the whole input and reproduce it. You give it part of the input, like these images, where there's a piece missing, and the goal is to generate that missing piece. So like if you have these family pictures with your ex-boyfriend or girlfriend, and you could just remove them from the picture, right? But what we want to do is we want to say, here's the receptor. The context is the binding site. Fill in a ligand that is the ideal ligand for this binding site. This is what we want to do, right? So given the receptor, generate a ligand. Right. So the way we are putting these together is in what we're calling, we probably need a better name here, the receptor-conditional ligand variational model. So you have the receptor, it comes in, and you have the ligand, and they form a latent space where the receptor latent space is distinct from the ligand latent space. So the idea here is you could vary the ligand latent space for the same receptor or vice versa, right? And if you have, during training, you can train it with the complex. So this is the actual receptor and the actual ligand, right? And then this is just sort of auto-encoding the ligand here with L2 loss. Or you can just sample from a distribution for this ligand space and generate new ligands. And that's where you use this concept of a GAN loss, right? Where you have to have a discriminator to basically evaluate, are these realistic looking ligand poses, right? And so you can put this all together. The architecture, we did some hyperparameter searches, you end up with the 3 levels, multi-convolutional levels, and you put them all together like this. And we are training on PDB refined, just existing poses, and we're using Caffe. We have our own fork of Caffe to deal with all this 3D and molecular data. We critically during training, we always randomly rotate. This is how we ameliorate the coordinate frame dependency of the grid representation, is we never show it the same grid. So it can't just learn, oh, there's something at this XYZ coordinate, therefore I will do this. So here is where we are as of last night. Certainly not going to be where we are if we ever publish, but I said I'd talk about it, so I'm talking about it. So this is the input. There's a receptor, there's a ligand, and the grids we're generating are matching the shape of the ligand for the most part in many of the atoms. This one is one of our favorite. I'm totally cherry picking, but the reason we like this one is it looks like a little car. You see it, there's a wheel, 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 wheel. Yeah, okay. Here's another one. Obviously it's missing key parts of the molecule here. It'll be kind of interesting to follow this up and see if these are actually important for the binding, if there's any structure activity about that, if it's actually highlighting the things that are important for binding or not. Here's another one. It's getting that ring, but totally missing this group, but getting the phosphate. So it's not bad. Well, it's not good either. And so we're still working on this, but of course the goal isn't to get blobs. We don't want to show a medicinal chemist a bunch of blobs. We want to show them a chemical structure. And so you can just fit atoms to these densities. And so if you take this car density and fit, you get this mess here, right? So the plan is to improve the output here so that even the simplest atom fitting density will produce something realistic. Backup plan is to start adding more and more physical constraints to this atom fitting optimization term. So for example, the lengths are right, the valences are right, the angles are right. And then you basically guarantee you get something the most realistic thing that fits the density. And there's actually opportunities here to generate multiple molecules. Having said all that, what we realized last week was that it's not, all of these things it's generating are completely determined by the receptor. That if we change this ligand latent vector, it doesn't really change the output. So we have some ideas where that's going, and we're going to keep working on it, and probably once we fix that, things will look much better. So that is a negative result. So I feel kind of like I'm in one of those European movies because I'm ending on a down note. So this is a little bit nicer. We are conditioning on the receptor. One way you can see that is the grid isn't changing here. I'm rotating the receptor, and you can see, of course, it's following the binding site and filling it in and getting slightly different densities there. Of course, you could argue you should be getting exactly the same densities, which we are. So I definitely need to acknowledge Matt. Is Matt here? There he is. So Matt's done, started as an undergrad. He's done all the generative work and a lot of the CNN work. So this is, you can talk to him. He's right there. I'm volunteering him to talk to you about this. Jocelyn did the GPU stuff. Paul is right next to Matt. He will be talking more about the stuff on the poster. He has a nice cross-docking data set. Here's the group. Here's the dog. Right. So, Jonathan's the other grad student who's here. He's also here, but he's doing something completely different with deep learning. And of course, I would not be here if it weren't for mostly the NIH and all the funding sources. If you want to know how to burn $40,000 of Google Cloud credits, I can tell you. That's also on the poster. And I'd be happy to take any questions, especially if you come to the poster sessions. Thank you. Sure.
Oh, yeah, really good work.
No, it's not. We're not done yet. Yeah.
It's really cool. It's like that you're pushing the boundaries. Really good. Thank you for the effort. What color channels are you using? So normally
it's atom type channels. Okay, so we're distinguishing the receptor and the ligand atom types. They are separate.
So my follow-up to that is you're accounting for rotational invariance. So do you account for electron density invariance in the sense that two functional groups could have different atoms but similar electron density?
No, it's basic atom types, and it's heavy atom types. We don't have hydrogens. We get the protonation by having different atom types. Electron density is something we've talked about, we want to work on, but I think that's a totally different training set than what we're doing here. It's a QM training set. Yeah.
A comment on the convergence behavior of the adversarial network.
Oh gosh, talk to Matt. Yeah, me too. I commiserate. We don't have a solution.
They run for a long time.
Yeah, because the goal, they're fighting each other, right? So you don't want anyone to be perfect because they have to still be standing to fight. Yeah.
It's just not as satisfying as like molecular mechanics with the basic protons.
Yeah.
One last question. Curious, so you're building the grid based on a single snapshot of the protein and the ligand, or do you do multiple monizations or move things around or anything like that?
Yeah, so in the current training set for all of this, and this is one of the things I think we're going to revisit to make this ligand variation thing more, but it is the crystal structure. The ligands, there's some variation in the ligands, but obviously not enough. And so like Paul made this nice cross-docking data set. I think that will help a lot. But we aren't doing dynamics now. All right. Let's see if anyone stole my seat. All right.
Let's thank the speaker one more time.
And just one announcement, we have 2 extra chairs here.